Hello everyone. In this video, I'm going to continue talking about Euler's method, but here I will do some examples. So let's start with this example here. Use Euler's method with step h equal to 0.1 to approximate the solution to this IVP, y prime equal x times square root of y at x equal 1.1, 1.2, 1.3, 1.4, 1.5. And of course, something is missing here. For this to be IVP, we need the initial condition. Okay. Okay. Let's do this one here. Y equal 4. All right. So if you look at the previous video, then Euler's process, we have xn plus 1 equal to xn plus the step h, and y of n plus 1 equal yn plus h times f of xn yn, with n starting 0, 1, 2, and so forth. So here, based on this initial condition, then x0, y0 point is 1, 4. Since we have the step h equal 0.1, that means, of course, x1 will be x0 plus h, which is 0. 1 plus 0.1, which is 1.1. And that's going to be the first point to evaluate here. Okay, so let's set up yn. So set up yn plus 1 equal to yn. The step is 0.1, and x1 we know 1, 4. Before going, let's leave it with n first. Let's talk about what is this f of xn, yn. Of course, it's this. Yeah. So x square root of y, and we'll put y xn square root of yn. So now that gives us the good this recursive equation to work with, and everything is known. So let's start with y1, which we need for x1, which is 1.1. So that's going to be y0 plus 0.1 x0 square root of y0. That's going to be a 4 from the point, and that's going to be x0 is 1, and square root of y0 is 4. All right, so square root of 4 is 2 times 0.1 plus 4, we get 4.2 for y1. And of course, this, if you put, of course, n equal 1, or just you say y1. All right, so what is the next thing? The next thing is x2, which is given. here. So let's calculate y2. And of course, you can use the symbol for approximation or equal. But but I think here usually in the equations I would write y2, and I'll show you the other tiny detail where to put the approximation symbol. Usually when, for example, you do this, then you do something like that, right? Because this is an approximation in this method. Okay, so y1 plus h f of x1 y1, and we know all this stuff. We just do 4.2 plus 0.1. F of x1, y1 is same, just to show again, it's x1 squared root of y1. We know x1 and y1, so 4.2 plus 0.1 times 1.1 times square root of 4.2, and with some calculation, y2, now rounding, I use that approximation thing, 0.540. So kind you get the idea, and from there, we can build the table. As you keep going, you can build the table. I'll give you the values, then I'll give you some more information so I understand more of this example. So let's say 1, 1.1, 1.2, 1.3, 1.4, and here is Euler's method. The answers came up to be, after that, 4.2, let's say 4.42543, 4.67787, 4.95904. I'll just add something here for you, that if we look, let's see a different color. If not skipping here, if we look for exact solution, we would find that that function is this way. And if we take this exact solution and calculate using these xn values, we would get these yn values as 4.21276 and 4.4521, 4.7976 and 5. Let's see. Okay, I paused and I added these values all the way to 0.5 or n equal 5, and added Euler's method answer and the exact solution answer there. So you can compare, and as you see, there is a residual, which means the difference between the two values, and but it still does a good job in the calculations. All right, so that's first example that will help you to see exactly how Euler's method is trying to calculate these solutions, and if it happens that we know the exact solution, we can compare as well. Okay, so let's give you a note. Of course, the step can be decided as you've done previously with the difference between x and x0 divided by how many steps you want or n desired steps. And in calculus 1, for integration, to use these rectangles, you've done something like that. Do you want to use 5 rectangles, 10 rectangles, and that decides what n is and decides the step. So if we wish, for example, if we wanted to approximate phi of 2, right, then using 10 steps, because in the previous problem, the step is given. But here, if you want to decide on your own, and you say, I want to use 10 steps, and let's say x0 starts at 1.5, then of course, all this under the note. Then h is going to minus 1.5 divided by 10, which gives you the step 0.05. So the main takeaway that is important to know, usually more steps, the better, right? However, also, it means more computations, which means it's going to cost something, more computations. And as you see, they're not exact answers, and it's recursive. You use the previous one in the next one, you use the previous one in the next one. So what does that tell you? There is a greater accumulated round-off error. So this is an important idea to know in general when you're working with these computations, and that the better doesn't mean kind of efficient. So you would need to decide how good or bad a method is based on kind of the cons and pros or the trade-offs. You're getting this for this trade-off, and you want to balance between the two. So in the next video, I'll do another example that's also interesting, and it's kind of connecting with this name of Euler method. So it would be nice to talk about the example that involves the number E. Okay.